Yeah, hello everyone. So I'm Nishant Garg at University of Illinois, and good to see many familiar faces in this room. Thank you so much for the organizers to organizing this very important session and giving me an opportunity to talk. So I'm going to talk about chlorellestadite. It's a bit of a mouthful to say. It comes from the elestadite family of minerals, and it's rich in chlorides, and that's why you have the chlor in front. And we're looking at how it carbonates in WTE ashes, which is waste to energy ashes. Okay, and before we go into all these kind of details, I want to maybe start off from a bit more broader perspective. And I don't have a meme for you today. I usually try to start with those, but I'm going to take a bit of a kind of a feel for the room, talk about waste management in general, right? We talk about recycled materials here. And if you think about waste production, as a species, as a human species, we produce a lot of waste. And this is very close to me. I grew up in India, and we just see waste everywhere. And we burn waste on the street all the time, and because there's just no way to manage this waste, and we continue to produce more and more, right? So I want to get a feel from the audience, right? And this is, I'm coming off, right, teaching the semester. I allow to ask quizzes to my students. I want to ask you, what do you think is the average waste production per person per day? Feel free to talk with your neighbor, discuss for 30 seconds, but don't use ChatGPT or the Google, okay, to get the answer. Use the neural network in your brain and see if you can think about it. And then we'll do a raise of hands for different options, okay? Your 30 seconds start now. Okay, so we now you want to. Right, so to stay good on time, let's see what you have here. How many people vote for option A? Raise your hands. Okay, nobody. How many people vote for option B? Raise your hands. Okay, so there's a good chunk here, 30 to 40%. How many people for C, raise your hands? Okay, there's about 30 to 40%. This is good, The answers here generally give me the idea of how optimistic or how pessimistic the audience is. Definitely nobody is optimistic, so you're right. If you tell you the real numbers here, this is the average over the world, right? On average, we're 0.74. But the min and max is also true, because there are countries who are on the min side, and there are countries on the max side. Guess where US or North America is on the max side. We produce a lot of waste, okay? And if you look at the global waste problem, this is what the projections are. This is millions of tons per year. If you put all the humans in the world on a big, giant weighing scale, that's where the human biomass will be, okay? So we produce much more waste than we actually weigh. Let's look at North America. Look at the human biomass of the United States. I should have pulled up Canadian numbers, but I'm from the US, so maybe some other time. All right, waste incineration. Let's look at some of the other countries. So one thing, you can do many things with the waste, right? You can always dump it into the ground, or you can burn it. And if you burn it, you have a waste incineration process, the waste to energy process, where you burn it, you generate energy. And if you look at certain countries on the far left here, Japan, Denmark, they're very limited in terms of their real estate to dump stuff in the ground. So they actually have quite a bit of high percentage of how much they burn it for energy. US, on the other hand, a lot of empty land, unless states like, we have certain states where the WTE facilities a lot. Previous speaker, Professor Ferraro, talked about the Florida. I think they're doing a great job in handling that. In the Northeast also, you see a lot of facilities. It roughly correlates with the population density, but there's also weird things happening, right? If you look at Minnesota and the state in the north, right, it has to do with some local regulations where you allow things to burn. And some people are like, well, we don't want our waste in this state. They ship it off to another state. It used to be shipped off to China several years ago, but in 2018, they kind of put a ban on that, and that has caused the industry a little bit of a scramble. We did some analysis of comparing WTE capacity with population density and landfill, and you can find this work online. It's kind of interesting way to look at waste management right now. Okay, we look at the waste to energy process, and we're going to specifically focus on fly ashes today. Again, Professor Ferraro talked about bottom ashes. We're going to talk about fly ashes. These are a smaller proportion of the output of the waste to energy process, but they're very nasty, right? They got a lot of heavy metals in them. By volume, they're also quite a big headache for the WTE plant to handle. And what happens is you have quite a bit of chlorides and lead in these systems, which cause a problem. So what we want to do is, if you want to use these ashes in something like concrete, we want to be very careful about corrosion and leaching risks. And what we have been working on is developing a treatment process to get rid of those nasty elements from these ashes out. So we did some studies here where we kind of look at the literature, what are the different compositions. So your fly ash and bottom ash, I'm talking about here the WTE ashes, is somewhere here on the spectrum, very similar to some of the other SCMs. We developed a very basic coefficient where we can start to predict the strength of these systems. Again, it's largely empirical, the incineration ash coefficient. You can find that online. But I don't want to spend too much time on this. And also there's another side thing where we do quite a bit of Raman imaging, and we can start to now see the actual minerals and species where the heavy metals are. Because you can know how much heavy metals you have in there, but knowing their speciation, right, where does it exist, is quite important. This is somewhere we've also been exploring Raman imaging for that. So for example, if you have lead and barium in cottonite and barite, you can target those minerals and selectively get them out. So the ash treatment process we have here is essentially a multi-step process. You essentially dissolve them, heat them, and filter them, and introduce them again to solution, and you result in an ash which is literally quite different from what you started with. And what happens in this heat treatment process, we form this mineral called chlorellestadite, which is a very interesting mineral. And again, I'm not going to spend too much time on the reaction kinetics, but you have to pay attention to the Ce mineral, which is a calcium silicon sulfate chloride-based system. And when we form this system, and if we measure the amount of lead in the ash, and this is an interesting slide, you see the amount of lead in the ash is actually increasing according to the top row as we do the steps. But what really matters is the leaching of the lead. So if you look at the TCLP lead mobility, it actually comes down by a significant amount, because that lead, we hypothesize, is getting trapped in this chlorellestadite phase. Okay. Now we say, well, if this chlorellestadite phase is any good, we try to put it into cement as a replacement. Unfortunately, it just turns out to be a filler. Right? You add 10%, it basically behaves like calcite. It doesn't do much for strength improvement, but it can take away the lead. That's a good thing. And then we start thinking, well, but this thing has a hell lot of calcium in it. Can we try to carbonate it, given there's so much interest in CO2? So what we then start to propose is, what if we took this chlorellestadite mineral, do CO2 curing in it, and consider some kind of a concrete block application? So then what we start to look at is, what is the mechanism by which CO2 gets trapped in this system? So we did some basic tests to figure out, again, how much CO2 you can get in there. And what we find is you can get on the order of, initially, these are the kinetics of how much CO2 that's get in there. It's about 7% from an experimental point of view. But if we do and then again, we did a bunch of testing to figure out what kind of phases form. But what we really want to know is, what is the mechanism by which CO2 is reacting? Because if we can understand that, we can increase the amount of CO2 that goes into this system. So we propose this kind of a detailed mechanism where we form this intermediate phase called calcium chlorosilicate. And I'm going to show you here kind of a step-by-step process. And again, this work is out there, so you can read the details there. But you start with chlorellestadite. You have CO2 and water. You have the 3 parallel reactions that happen. You have the first reaction where you have these hydration products. In the second reaction, your calcium chlorosilicate, which again is a kind of a very interesting phase. I think it's worth looking into. It forms sinjarite and calcium carbonate. And the sinjarite, which is calcium chloride plus H2O, forms finally calcium chloride and hydrochloric acid. Right? And if you calculate the theoretical CO2 uptake for chlorellestadite, it's actually around on the order of 30% if those reactions go to completion. Compared to some of the others, it's definitely in the lower end. But if you consider some of the SCMs people are trying to carbonate, they are actually on the order of 2 to 3% or 5%. So it's 30%, I would say, still not a bad deal, considering this is completely a waste material. So if you take waste materials and start to carbonate them, the cost is going to be very low, because people are paying to get rid of these ashes as of today. Now, if you look at this idea of what happens as you simultaneously carbonate and hydrate these systems, you can actually see, you now start to see chlorellestadite actually starts to give strength. So by adding 20%, by diluting the clinker by 20%, you actually get a boost in strength compared to the control cement. So I think this is now very, very interesting. This paper is currently under review, so hopefully later this year is out. Okay, so in terms of an outlook, I think what we have here is a couple of main conclusions where we say that you are able to store about 30% CO2 by weight. We have 3 parallel reactions that we have disclosed, and the exact mechanism can be used to enhance the strength of cementitious systems when you simultaneously carbonate and hydrate them. Okay? And again, all of this work is out over the past few years, except the last one, which is going to hopefully come out this year. These are some of the relevant publications. You're welcome to take photos of these, and you can find them online if you want PDF copies. If you don't have access to them, they're behind paywall, just email me. So with that, I want to acknowledge my group, specifically one of my PhD students, Vikram, who led this work, as well as Mohammed, a master's student, who also helped quite a bit. I want to thank the funding agencies. There was a project from ARPA-E which largely covered the funding of this, and one of the papers that came out was on the cover of one of the journals, so we're very excited to kind of put this out.